and welcome to Computer Science 732 Information Security. This is Lecture 3 on Programming Errors, where if you're following along the book, it is Flieger Chapter 3. Alright, so we're going to talk about software problems, and then we'll look at a whole bunch of vulnerabilities that have cropped up across over the years. So keep in mind, programs are widely used and have become very complicated. Most users of these programs just don't understand how they work. Many programs have failed spectacularly and continue to do so. Typically, users really don't know whether a program is producing correct results or not, so it's because they're so complicated. Two consequences of program flaws are that you can have incorrect results, so that's a failure of integrity, and so if a faulty program may modify some correct data that was previously around. There was probably no malice, but quality of the system is affected by these flaws. We'll define what flaws and failures and errors are in just a second. But first you want to just get a quick view of what happens when you have program flaws. So one type of flaw can just give you incorrect results. It may not actually affect the security, but it might. Another type of flaw is one that could be exploited by an attacker, a threat. So in this case, a benign flaw can now become a vulnerability to the security of a system. For both kinds of flaws, program correctness is now a security issue. So one example of a flaw is one that happened with the Mars Global Surveyor. There was an update to fix a relatively benign precision problem, and that unleashed a cascade of errors. So what happened was there was a way to write things to two variables, antenna and solar. If you write the data item, and if you write to a data item and it overwrites the antenna and solar settings, then what happens is there was a whole bunch of sequence of events that ended up with spacecraft being unable to respond to any signals from Earth. So if you want to go down to the sequence of errors, if you wrote to a data item, it would override two variables. One of them made the solar array over pivot. That generated alarms, which resulted in the battery overheating. So the solar array was tilted, I guess, too far towards the sun. And as a result of the battery overheating, the recharges stopped, then the battery died, an alternate battery was overworked and died. And then the antenna, as a result of the battery being overworked, the antenna got misaligned. There were no signals coming in from Earth, and you could not reorient the solar array to fix the step 2, the error 2. So it seemed like a relatively benign change, but it ended up causing a cascade of errors, eventually leaving the spacecraft just unusable, essentially. Okay, so now let's take a look at some of these terms: flaws, faults, failures, and errors. So I've highlighted them put them in red just to draw your attention to these terms. You want to understand exactly what they mean, because I think they're often used in ways that are probably not compatible with the way we try to use it in security. A flaw is a problem with a program. A security flaw is a problem that affects security. So the things you want are confidentiality, integrity, and availability. So these three things will come up over and over again. So if you're following along in the notes, there's a link to the IEEE 610 standard from 1990 that defines all these terms. So you can actually click on this link and it'll take you to the IEEE document. So humans make errors. Computers actually don't make errors. They do exactly what we tell them to do. It's kind of hard to believe, but that's actually what happens. Computers actually have faults or failures. And a fault is not an error. A fault is a mistake due to an error in coding, design, or documentation. It's something on the inside of a system that can lead to a failure on the outside, or the user view of a system. A failure, on the other hand, is a departure from a system's required behaviors. So you have a set of required behaviors, and if a system doesn't follow those required behaviors, then you say that you have a failure, and that could be due to a hardware failure too. Okay, so I hope these 4 terms make sense: flaws, errors, faults, and failures. They have very specific meanings. Some flaws are unintentional, or human errors, or now we're talking about security flaws. So it's possible that you might make a mistake, a human makes a mistake unintentionally, and then you end up with a flaw. A flaw can be intentional, that is a malicious flaw intentionally placed to attack a system, or it might be a non-malicious, so it's no bad intent behind this flaw, and it may be a feature that's correctly implemented, but one that can be used by an attacker to cause a failure. So maybe there was no malicious intent with this flaw, but then it could be a vulnerability that can be used by an attacker. Many security flaws are actually caused by unintentional program errors. So a classic example is buffer overflows, and we'll go over what buffer overflows are. The other example that's in the book is incomplete mediation, which really just means not enough checking. So mediation is really just another word for checking in this instance, in this context. Another type of security flaw that's caused by unintentional errors is time of check to time of use, or race condition. So this is where you have multiple things happening at the same time, and then depending on which thing happens to usually write to some area of memory or file or something, different things will happen, maybe unintended consequences. Okay, so let's take a look at buffer overflows first. So you've probably all seen things like this. This is C code, and so you have, the first line tells you that you have a character array of 100 elements called buffer, so that's 100 bytes. And then what you're doing is you're copying into that buffer something that you're getting from the command line argument. So if you type in, you could type in, so you're taking argv sub 1. So if you're not familiar with C, you type in a command or run the program with a space and then another command line argument. And if that's just, let's say, 10 bytes or 10 characters, you'll copy 10 characters into the buffer. However, there's nothing stopping you in a program like this from entering 50 characters or 100 or more characters. So you could type in 110 characters. And this string copy function will take all of those, let's say 120 characters or 150 characters, and try to copy that into the buffer. So that's really where this problem comes up in C. Not so much a problem in other programming languages, but in C, this function strcpy does not check whether the string being copied, which is argv sub 1, which is a string, a long string, whether it will fit in that buffer variable called buffer. If it is too big, a lot of languages, like Java, for example, will throw an exception and could result in the program crashing because of that exception. So in Java, you might have all seen array index out of bounds exception. So that's what happens in Java, but in C, there's no such exception. In C, it just keeps going, and you just overwrite whatever is past the bounds of this buffer variable. And so there's many things that could be there beyond the bounds of the 100 spaces for buffer. So let's say this is a schematic view of the buffer variable. It's a lot less than 100, of course, but just to show you what could happen. So let's say you have some data, and then you override it, well, you don't know what's beyond the bounds of that array. In Java, of course, as soon as you go beyond the bounds, your program throws an exception, program crashes, does not do anything to what's on this end of that buffer. However, in C, if you have program code, that gets overwritten. That's dangerous because you could start executing code that was put there as a result of this buffer overflow. You could have system data. Often if you have system or kernel data, when you go beyond the bounds, you could go beyond the bounds a little bit, but once you get into system data, usually there is a trap or a problem that the kernel flags, and it'll kill your program. And then the same thing with if you have system program code, if you write over something to do with the kernel, or it could be part of the kernel or a library function or something, often those things will get caught eventually. So usually what happens is you can exploit the fact that if you have the user's program code, you could override it quite a ways and not get in trouble. It used to be that this would not cause problems, but a lot of these security holes actually have been fixed by now. So attackers in the past, they have used this problem where you can basically overflow the bounds of a buffer and attack systems in many ways, and we'll see some of these. So we'll look at buffer overflows in just a little bit, but first let's take a look at some overflow errors too. So errors can be a lot simpler than what we've looked at with buffer overflows. Number values can also overflow. So if you have something as simple as an addition, so you're saying an int c is equal to a plus b, and you assume that a and b are ints, what could possibly go wrong? Well, it turns out an int only holds 4 bytes, and so there is a maximum value which is about a little bit more than 2 billion, and then a minimum value is negative 2 billion roughly. It's a little bit bigger than that. But it goes roughly the maximum size of an int, maximum size of the values that an int can hold go between negative 2 billion and positive 2 billion roughly. So then in that case, what could go wrong with addition? Well, these could be both, a little bit more than 1 billion, let's say 1.5 billion. You add two numbers that are way too big to fit in an int, and so you add two positive numbers and you can get a negative number. So that actually does happen. That's called a int overflow, a number overflow. Java 8 actually has a fix for this. It's a method called math.addExtract. So if you're following along the notes, just click on this link. It'll take you to the page in the web page in the Java 8 API. It's pretty nice. So ordinary Java, if you just use the operator to add these two numbers, yeah, you will get an overflow. But it doesn't cause an exception. So there are languages that can trigger an exception when you overflow. But C, regular Java with just the operator, the addition operator, this ends up being an overflow, but no error, no exception. Okay, so we saw how even the simplest possible operation, probably just adding two numbers, can give you overflow errors. The more complicated problems that programs run into are things like incomplete mediation. So what is mediation? In the context of this chapter and basically security in general, mediation means checking. So it's the process of intervening to confirm a subject's authorization before taking an action. So it's like verifying that a subject is authorized to perform an operation on an object. Okay, so if you have incomplete mediation, what that means is that you're not checking as much as you should. That happens a lot. So for example, you might have inputs to programs that can be specified by, let's say, untrusted users, for example, using a web app. So a web app might have various text fields that you can enter stuff, and users can mistype or enter the wrong data, probably unintentionally. Like this, you might have you might be expecting an email address, which is usually some string followed by a @ sign and then a fully qualified domain name or an IP address, usually fully qualified symbolic name. And so if the user enters a hashtag instead of @ sign, then, or a hash sign or pound symbol, then chances are the web app probably will store that, but then later down the line it might cause problems when it tries to send an email, let's say, to that address. Another possibility is an entry for a phone number might have way too long a string. If there's not enough checking, this might not get caught. This might not have been malicious, might have just been that the user had his or her hand on the key for 5 just a bit too long, and it repeated that and repeated the 3, and as a result you went way beyond what a phone number should be. If you're not checking the length of a phone number on the server side or in JavaScript on the client side, then this could cause problems down the line. So this is incomplete mediation, just not enough checking. If you take in any number, any date of birth or date without checking it, those are all examples of incomplete mediation. So what should happen is a program, mostly that's a web app, should ensure that what a user has entered is a meaningful and allowed request. So that's what mediation means. Incomplete mediation occurs when a program accepts incorrect data from a user. So they're often easy to overlook. So for example, I try to put in my number, and I've done this before. I put in the area code, and then instead of typing in 425, I type in the wrong number 5, and such a number may not even exist. Sort of looks okay, but could be wrong. Date of birth, I don't know if you spotted the problem here, but there is no February 31st. This is just not possible. So it looks okay on the surface, but then if you don't check this, you could have problems down the line. You could do mediation on the client side. So when you enter some invalid data in a web app, and then you could have a pop-up stop you from submitting the data. So that is, you could have JavaScript code in the browser, that is on the client side. It might check your data, check the data that the client enters, and then flag it if there's problems. However, even if you do stuff in JavaScript, you can have problems if, for whatever reason, the user turns JavaScript off. So these days, that's less and less likely that the user will turn JavaScript off. But if there are people who are very concerned about security, they might just do that. They might just turn JavaScript off, which means the code in the browser won't be able to check stuff, and then a lot of things won't work. Also, you can connect to a server manually. So you can, from the terminal, you can say telnet web app or whatever website you have, and then use port 80 or port 8080 or 443, and then you'll get all of the output coming from the web app just on the screen. That is in a terminal window rather than a browser. So although the output of web apps is supposed to usually be displayed in a browser, so you might actually have someone looking at all this data on a terminal screen, and then they might have a custom program to parse that and then send off a response using that output. You could also have a script to send data instead of a web browser. So there's many things that could actually go sort of sidestep this even if you have some kind of checking with JavaScript on the client side, it's possible that you can bypass all those checks. Okay, so there are problems with web app URLs too. So suppose we have the following URL in a Java web app. Here is how you parse such a URL. You start with a fully qualified domain name, and usually you have www.domain name, and then you have the path to some, let's say, servlet code. In this case, we're looking at JSP, Java server pages. If you're not familiar with Java server pages, it's not a big deal. For the main part, all you have to remember is that you can have basically something executing on the server side. That's what this is. And then some input to that server-side code. In this case, it's a query string asking for matches of account that have the word Chris in them, or something like that. So there could be many problems with such a query string. What if we were expecting a number rather than a sequence of letters? So rather than letters, let's say we were expecting an account ID. It's not obvious. What will happen if for whatever reason, somehow, that the user using a browser was able to send off this web request? Will the web app fail completely? Will it crash? Or will it just detect some bad input and then handle that somehow? So if you're not checking for this, that's incomplete mediation, and your app may crash and reveal information about the app itself. Okay, so once again, you have a server name, then a path to some servlet code, and then maybe a query string. And so what you do is you by packing the result into such a return URL program, the programmer might possibly leave these fields in a place where the user can access them and modify them. And so if you see this in your address bar, URL bar, what would happen if the user goes up here and backtracks or deletes these characters and puts in Tom instead or something like that? Would they actually be able to switch from looking at the Sujay account to the Tom account, which maybe they're not supposed to see? Maybe Tom is a system admin and you're not supposed to get this information. But if the user can edit the URL, what happens? You might have to have some server-side checking to make sure that the user cannot arbitrarily change these fields. Okay. Typically, client-side mediation is good for user friendliness. So you do a lot of checking on the browser side to make sure that your web app is usable, but usually you don't do security checking on the browser side. And what you typically want to do that is a good defense against incomplete mediation is to server-side mediation. Whether or not you don't bother about whether you do client-side checking or not, you just have to do server-side mediation on the server to make sure that you have good defenses against incomplete mediation. And basically you want to always check every value in every field. So date of birth, telephone numbers, emails, all of these things you want to check, make sure they're within valid ranges. So we'll get back to incomplete mediation later on, but for now, the main thing you want to take away is that definitely check every single value in every field on the server side to be completely safe. There's a lot of cases I have seen myself in, for example, in my bank's web app, I could make it crash, and when it does crash, it gives me a SQL error and revealing a lot of information about what it's doing on the back end. That should not happen, just should not happen. If you ever see that, you probably want to send them a message saying, look, this is what your app is doing, and you should probably get them to stop it, because that could be a potential security flaw. Okay, so I'm going to stop here for a second and start another video right after this.